One of the most fundamental things that we're going to need to do when we talk about integration in multivariable calculus is the notion of double summations. We're going to be adding up a bunch of things, and we're going to have an x and a y component that we're going to need to sum across. So as a result, we want to begin thinking about how we could do this. And let's just start with a basic example where we want to find the sum of the product of every x with every y in the table below. So what we mean by that is we want to find, for example, here this value is x sub 0. So x sub 0, by the way, is 5, and y sub 0 is 2. And that's what we're doing here with the indices. So x0, y0, x1, y1, x2, y2. We're going to label these with indices because we're going to run out of letters if we try to give every single value a separate variable name. So let's think about how this would work. So we would want to do x0, multiply that with y0, then add to that x0 times y1, and then x0 times y3. So what that might look like is x0 times y0 plus x0 times y1 plus x0 times y3, and that would be 10 plus 20 plus 30. And that gives me 60. So that's just me summing the first x with all of the y's. Now I would want to do the same thing, but instead of with x0, I'm going to do it with x1. So we'll do 10 times 2 plus 10 times 4 plus 10 times 6. So this will be x1 times y0 plus x1 times y1 plus x1 times y3. And that's 20 plus 40 plus 60. 20 plus 40 plus 60, which is 120. And then I want to do the same thing, but now with x3, rather x2, the third value of x, and it's just pretty customary to start with a subscript of 0. We won't get into the details of why, but you'll notice that a lot of times we start with indexing by 0. So here I'll have x2 multiplied with y0 plus x2 multiplied with y1 plus x2 multiplied with y2. And I think I used 3 over here. This should be 2 in both these instances. And that will give me 30 plus 60 plus 90. And that will come out to, let's see, 150, 180. And then I want to sum up all of the products. So each of these lines just summed up one value of x with all the y's. And when I sum these together, I'll get 360. Okay, well, with this double summation, the way we could do this is we could say, let's add up all of the products where j goes from 0 to 2. So my smallest index is 0, my largest index is 2. And then sum up all of those. So think about this first line as basically producing our 3 lines here, but then we want to sum all those up. So we want to sum up across all of the i's from 0 to 2. And what do we want? We want xi times yj. Okay, so here's how a double summation works. First of all, the outer value sets the first index value. So this one will set I equals 0. This next one will also start off at the lowest index, which will be j equals 0, and it will multiply those two values together. So basically, x0 times y0. Okay, so now what happens is because now we have that term in our sum so far, the inner sum is always the one that changes its index value first until it runs out of values. So now this one will change to j equals 1, so that means now we'll add to this x0 times y1. Now that we've accounted for that term, j changes to 2, and now we have plus x0 times y2. But we're going to continue adding, so I'll just put this in parentheses just to emphasize that that's really the first line, that's really what we came up with here. But now we continue adding, but because we've run out of j values, we're at j equals 2, this one now resets back to 0. But this outer index now becomes I equals 1 because we've run out of j values for I equals 0. So now I becomes 1, j resets to 0, and now we add to that x1 times y0. And now j increments again, j becomes 1. We have plus x1 times y1. And now j becomes 2, and we multiply x2, y2. x1, y2. Always summing as we go. We're adding up all of these components. So there's x1, y2. But we're not done adding, because now that we've run out of index values for j, now we come back over to I and say, okay, now I can still go up to 2, so I will become 2. J will reset to 0. And now we'll have x2 times y0. Now j will increment again to 1. So now we have plus x2 times y1. And j has room to grow still, so we'll make this I equals 2, j equals 2, and so we'll be adding x2 times y2. And you can see that each of these parenthetical expressions represents one of our lines in this table up here, and if we add these together, we're going to get, well, 360. So this comes out to 360. Now that's how I chose to do it in this sum, but I started, my inner index was for the j value, and we could also rotate these around, meaning we didn't have to have I be the outer sum and j be the inner sum. What we also could have done, so this is an alternate way, we could have summed up by saying, let the inner index go from I equals 0 to 2, and then the outer sum from j equals 0 to 2 of the xi times yj. You could rearrange their order. You could do yj times xi, but there's no need to because multiplication is the same both ways. So once again, we kind of think about the inner index as running its course from I equals 0 to I equals 2, and every time we hit 2 on the inner index, the value of j increments again by 1. So, create a little bit more space here. First of all, we look at the outer index, it becomes 0, and now the inner index becomes 0, and so what this means is that we're going to add x0 times y0. But what we're going to add to that is now the value of the inner index, which is always true. The inner index always increments before the outer one does until it runs out of values, until it gets to its max of 2. So now we'll do j is 0, I is 1. So this is really x1, because I is the index for x, and j is the index for y. So this will be x1 times y0, because j is 0, plus the value of I will again increment to 2, and this will be x2 times y0. And now we're done with that inner index because it's reached its highest value of 2. So now j resets, or I shouldn't say resets, but increments to 1, and I resets to 0. So now we're going to add to that x0 times y1. The index increments again. I becomes 1, j is 1. So this is plus x1 times y1. Whoops, one more term there. So the value of I is now 2. So x2, y1. And now that takes care of our I has run out of index values, so now j will increment to 2, I will reset back to 0, and this will become x0 times y2 plus I becomes 1. So now this is going to be x1, y2 plus, last term is going to be I equals 2. This is going to be x2 times y2. Now this looks different than the previous sum, but we could go term by term and identify what we have down here in comparison to what we have up here. So let me label these. We'll call this term A, So term A is right there. Term B here, x1, y0, doesn't appear until the second set of summation here. And x2, y0, which we'll label C, is right there, x2, y0. So these things are all being added together. It doesn't matter what order they're added together in. And now x0, y1, we'll call that D. So here's x0, y1. We'll call x1, y1, E. So you can kind of see that we're adding the same terms, but we're kind of taking one term from each of these parenthetical expressions at a time and adding them together down here. And then now we have x0, y2, which I'll just call G. So there's G plus H, x1, y2. There's H right there. And plus, we'll call this I. x2, y2 is right there. And you can see that we've added together all the same terms. So this is going to come out to 360. So how does this apply to integration? Well, with integration, what we're going to do is we have already noticed in our applet to demonstrate is that we have some sort of surface that's lying on top of this graph, which probably looks something like this. It could be some sort of wave-like surface. And what we're trying to do is we're trying to approximate the area underneath, or rather the volume underneath that surface for the range of x from 0 to whatever this value is, and from y equals 0 to whatever value of y this is. And you can see here that this picture just has more rectangles, or more prisms, more rectangular prisms. And so this is going to give us a better estimate, just like having more rectangles in two-dimensional calculus would. So what do we want to do for each one of these French fries? Well, each one of these French fries has its own volume, and the sum of all of those volumes is precisely what gives us the overall volume estimate. So if we kind of imagine this one French fry, here I'm going to draw this French fry, and this French fry has a depth to it, right? So there's that depth, and that's just one of those French fries. And this base right here, which is the same thing as the bottom one, there's the bottom one. This has a dimension of, well, one of these components is going to be the delta x. We'll just say that that piece right there is delta x. We'll say that this piece right here is delta y. So in order to get volume, we need to get the area of that little square, and then multiply it by its height, which is f of x comma y. So here you can see that we just have height times, I guess we can call this length, times width. Does not matter what order those are multiplied in. Does not change the summation. But what we need to do is we need to add up along all of the y's and along all of the delta x's. So in this context here, if you notice from our sum up above, when we had the j index first up here, we went through all of the j indices. So if I sum up across all y's before incrementing to my next delta x, I'm going to add up all of the delta y's. So what this is going to look like is I am first going to move and add up all of the volumes of these prisms going from front to back. All of these volumes I'm going to add up in this particular order if I do the sum with y going first. I'm going to do all the delta y. Oh, I'm sorry, we have this backwards. This is the y-axis. Let me try that again. So we're going to do all the delta y. So y goes in this left to right direction. So we're going to add together the volumes of these French fries in this order. We're going to go in this direction, add up all of those, then move to the next row, add up all of those volumes, and then we're going to end up adding up all the way to the back row, adding up those volumes as the final row. Now, however, when we do it this way, when we add up across delta x first, you guessed it, we're going to add up across all of the x's, so basically add up all of these columns, and we're going to do it row by row. So in the second variation here, and I just kind of copied those images so that we have the perspective, again here we're going to add across all of the delta y's, and only then, once we've added across all of the delta y's, once we've done that, then we move to the next delta x. and we continue adding. So what that will mean is that when you change your delta x, so this first one here, that could be your first delta x, and then your second delta x, and your third delta x, that's basically taking us one row at a time. But when we do it this other way, when we say, okay, add across all of the delta x first and only then move to the next delta y. Well, all the delta x's go backwards this way, so that means we're going to sum all of these guys here and then move to the next y, the next delta y. So here's kind of, you can think about that as the first delta y, and then the next delta y, we're going to do the same thing. We're going to add up all of those volumes there until we reach the back row, or the back column, I should say. There we go. And so once we add those up, that will take care of this sum. But the important part to note is if I added the volumes in this order versus if I added the volumes in this order, I would get exactly the same answer. So the order in which you add those volumes is not important. So why do we propose two sums? Having two sums is actually really beneficial because these are going to become integrals. When we make delta x and delta y infinitesimally small, we are sometimes going to find that doing the integral or setting up the integral one way is going to be easier than setting it up the other way. And we'll see that not in this lesson, but in the next one. So here's a real-world example. The fox population in parts of England is important to public health officials concerned about the disease rabies, which is spread by animals. Biologists use a contour diagram to display the fox population density, D. So we can think about that as the number of foxes per square kilometer. And there we go. So that's going to be in foxes per square kilometer. The bold contour is the coastline, which may be thought of as the D equals 0 contour. Clearly the density is 0 outside D equals f of x, y, where x and y are in kilometers from the southwest corner of the map. So here's the southwest corner. Okay, so clearly like in this box here, there's not going to be any foxes, but there's going to be quite a few more here where we have this contour of 2. So I'm just going to propose that we set this up for now for simplicity. We're going to break this up into 2 regions. So one region going that way, and then we'll break this up down the middle. So basically we create 4 separate rectangles. And I am just going to go ahead and default to using the, we have to pick a population density. So first of all, each one of these regions, in terms of how many square kilometers it is, this region here, that is our, you can think about that as the delta y, and delta y is from 75 to 150, so it's equal to 75. And that's true for this one down here as well. Delta y is 75. This delta x is equal to 90 because we've parsed up our rectangles into 90 units across the x-axis, and same thing here. This will be delta x equals 90. Now all of these are in kilometers, so we should probably label that as well. And when we multiply kilometers by kilometers, we'll get square kilometers. And if we can come up with an estimate of how many foxes there are per square kilometer, then we can multiply foxes per square kilometer multiplied by how many square kilometers we have in that region will give me foxes. And that's exactly what I want to estimate. So not only are integrals useful for computing volumes, but they help us add things together that we want to add together. So how do we, within each of these 4 regions, we know we're going to be off because we see that the number of fox, for example, in this northeast rectangle that we've created varies wildly from 0.5 all the way up to 2. So for simplicity, I am just going to pick the highest number of foxes. I want an overestimate. So for an overestimate, I will pick the highest number of foxes within each of the rectangles. So I'm going to call this down here rectangle 1. Now in rectangle 1, I see that the highest contour is actually 2 because part of it comes into that rectangle. So I'm going to assume that rectangle 1 is going to have, well, let's see, that's going to be 75 kilometers by 75 kilometers, or by 90 kilometers, excuse me. times 90 kilometers. And now we need to multiply that by the number of foxes per square kilometer, which we've come up with an overestimate of 2 foxes per square kilometer. And when we multiply those together, we get 75 times 90 times 2 comes out to 3,500 foxes. And now I'm going to repeat the same thing. I'm going to do it for, we'll just jump up to this region here. And so that will be, again, 75 kilometers by 90 kilometers. And the greatest number of foxes I have in this region, I'm not going to count that corner point. I'm just going to say it's 1 because that's most visibly the highest density of foxes that I have in that region. So I'll multiply this by 1 foxes per square kilometer. And that's going to give me, let's see, divided by 2, 675 foxes. And then we have 2 more regions. So we have region, I'll call this region 3, and I see that that highest contour is a 2 there. So this will be 75 by 90 by, what do we say, 2 foxes per kilometer squared, which comes out to the same as the first one, 1,350 foxes. And region 4, I'll do the same thing. Here's region 4, and I again see the contour of 2. I'm going for an overestimate here. So 75 kilometers by 90 kilometers by 2 foxes per square kilometer. That's going to give me, once again, 1,350 foxes. Now I want the total. So when I add those together, that will give me my overestimate for this entire 180 by 150 kilometer region, square kilometer region, and this is going to be 4,720 foxes. Now, how could I have come up with this as a double sum? So to be very specific, we could say that we used a sum. Well, there are 2 ways. We could sum across, if we think about this as the x and this is the y-axis, then we could first of all decide to sum from, let's see, I equals 0 to I equals 1. So think about this as I equals 0 and I equals 1. We could, you know what, let's take away the indices altogether. We're not going to worry too much about that because we're not really going to need it. We'll just say we're going to add across all x, and then we'll add across all y. And what are we going to add? Well, we're going to add the delta x by the delta y multiplied with the f of x, y at that point, which was, in this case, the number of foxes. This was foxes per kilometer squared times kilometers leaves me with foxes. And so if we added it in this order, we'd be adding across all the delta x's first for the initial delta y. So what would that have been in terms of our summations here? Well, that would have been region 1 plus the number of foxes in region 3 because we're moving across all the x's first, then we'll increment y, and now we're moving up to this top portion here and we're going to add region 2 and region 4 to that sum. If I had done it the other way, if I had added across all y and then across all x like this, of f of xy, the number of fox per square kilometer, times delta x times delta y, I would be adding, well, first of all, I'd go across all, I just wrote down the same thing twice. This is delta x and this is delta y. And that's delta y. So I would be adding basically across all the delta y first for the initial delta x. So here's my first delta x. It's this region between 0 and 90. And I'm going to add upwards. So I'm going to add region 1 plus region 2 because I'm adding across all the delta y. And only then will I move to the next delta x, which is this region between 90 and 180. And now that's going to entail adding region 3's fox's estimate and region 4's fox's estimate. And you can see that these are identical, that these two things are equal to one another. We're just adding in different orders. Okay, so in each of these cases we get 4,725 foxes. So to get an exact volume, you can probably see where this is going. We're going to take the limit as delta x and delta y both become infinitesimally small. So if I write the limit as delta x approaches 0, and we can write it like this, as delta y also approaches 0, of the sum in either order, delta y first or delta x first, of f of xy times delta x delta y, right? I'm going to make these guys infinitesimally small. By the way, this is actually what we would call as the change in area, or delta A, because that is a small patch of area. So as this happens, what this is going to become, well, as we make delta x infinitesimally small, we call it dx. As we make delta y infinitesimally small, we call it dy. The function stays the same, and guess what these guys are? These are integral signs. And if x goes from a to b, this first integral on the inside is my x from a to b. And now my value of y goes from c to d, so this is y equals c to y equals d. And sometimes we compactify, we compact these things into a smaller notation just for the sake of brevity. And we will often write this as, this is really just summing across the entire region R. Remember, the region R is the portion of our xy plane where we want to find a volume, or in the case of foxes, we want to find the total number of foxes. So we're going to compact that symbol down to the integral over the entire region, which really is a double integral. It's two integrals of f of xy. And now dx dy, you'll often see us refer to that as dA. That's really just the infinitesimally small area that we're getting up here. And we can do these in either order. So if I want to sum across x first, I could do that. So I could do from x equals a to x equals b, the sum from y equals c to y equals d of f of xy, dy dx. Or I could do it another way, which is to sum from y equals c to y equals d, x equals a to x equals b of f of xy. But this one's going to be dx dy. Now, the difference, and this is called an iterated integral, because when we're stepping through all these indices, what we're doing is we're iterating. This process of changing the index is called iteration. And what's the consequence of doing it this way versus this way? Well, in this one, you're gonna basically do the integral with respect to y first, and then whatever answer you get here, whatever answer we get there, then we're going to integrate that with respect to x. Here, we're going to integrate with respect to x first, and then once that's done, whatever is left over, we're going to integrate that with respect to y. So let's actually do it for our volume under that constant region, f of xy equals 4, over the region where x is between 0 and 4 and y is between 0 and 5. So if we remember what that looked like, we had x going from 0 to 4. So 0 to 4, and y going from 0 to 5. And we wanted the volume underneath that surface. Remember, the surface is coming directly out at us in the screen. The z-axis is being kind of mashed down into the xy plane. And we want to find the volume across this entire region. So remember, our f of xy here is 4. So what we're going to do, and we're going to set this up two ways. The first way is to sum from x equals 0 to x equals 4. And then take the integral from y equals 0 to y equals 5 of our function, f of xy. And since x is the inner integral, this is going to be dx dy. So if we do this integral, here's how this is going to work. Now, f of xy, recall that's equal to 4 for our particular example that we started off with. And so we're going to conduct the inner integral first. So that means that I am going to integrate with respect to x initially. So the integral of 4 dx is 4x. And that's going to go from x equals 0 to x equals 4. Okay, now I still have the outer integral here as well, that one from y equals 0 to y equals 5. So I'm still going to integrate this from y equals 0 to y equals 5, but I'm only going to do one at a time. And so I still have this integral dy. And when I was referring to whatever's left over once you complete this inner integral, which in our case is going to be 4x evaluated at 4 and evaluated at 0. It's still the same fundamental theorem of calculus. This is going to come out to the integral from y equals 0 to y equals 5. We're going to evaluate 4x at 4 minus 4x evaluated at 0. And whatever answer we get there, now we're going to integrate that with respect to y. So this is pretty cool stuff. Here we go. And now that's going to come out to the integral from y equals 0 to y equals 5. This comes out to 16 minus 0, which is 16. And now all I'm going to do is integrate 16 with respect to y. So if my variable is called y, this is going to be 16y is the integral of 16. If this was dx, this would be 16x. If this was dw, this would become 16w. And so the integral of 16 dy is 16y, evaluated from y equals 0 to y equals 5. And that comes out to 16 times 5 minus 16 times 0. So this equals 16 times 5 minus 16 times 0. And guess what? 16 times 5 is 80. What are the units of this thing? Well, we multiplied a unit by another unit by another unit, and if we multiply unit times unit times unit, we get cubic units. So this will be 80 units cubed. And we could have done that integral, instead of doing dx as the inner and dy as the outer, we could have reversed those just to see that we get the same answer. Let me move this down a bit. So our second option would have been to say, or we could have integrated from y equals 0 to y equals 5 of 4 dy, and then integrate that result from x equals 0 to x equals 4 of dx, that function dx. So we're always going to focus on the inner one first, and the integral of 4 dy comes out to 4y evaluated at y equals 0 and y equals 5. And then the integral of that thing from x equals 0 to x equals 4 dx. If we evaluate this at 5, we get 20. We evaluate it at 0, we get 0. 20 minus 0 is 20. So now we're going to integrate the constant function x equals, constant function 20 from x equals 0 to x equals 4 dx. And the integral of 20 is going to be 20x. And so this comes out to 20x from x equals 0 to x equals 4. And if you plug in 20 for x, you get 20 times 4 is 80, minus 0 is 80. And again, we get 80 units cubed. Perfect. So that gives us the same answer. Obviously, we didn't need to use integrals, but this just shows that it works. For our second example that will work, let's pick something that is not a constant function. So notice that now our f of xy has both x and y in it. So how do we integrate a function with variables? Well, whatever we're integrating with respect to, hold the other thing constant. Okay, so let's go ahead and carry this out. And here I've just written, if integrating dx, treat y as a constant. If integrating dy, treat x as a constant. So just like when we're taking partial derivatives. So notice our region is still the same. X goes from 0 to 4, y goes from 0 to 5. So if I want to do my inner integral as the dx, this one's going to go from x equals 0 to x equals 4 of my function, x squared plus y squared. And then, of course, this is going to have to be dx. And then after that, so I'm going to add up across all of the x's, all of the dx's, we think about what that means, we have to come back up here and look at our little pictures. If we're integrating dx first, we're going to be basically adding up all of the volumes of all of the columns. If we're integrating dy first, we're going to be adding up all of the rows first, based on these two pictures. So let's go ahead and carry this out. And this is going to be from y equals 0 to y equals 5 dy. Okay, so here we go. So to compute this guy with the integral of this guy with respect to x, well, I know that the integral of x squared is 1/3 x cubed. And now y squared is being treated as a constant. So if this is a constant right here, then that means, think of this like you would the number 3. Well, what's the integral of 3 with respect to x? It would be 3x. So because this is an integral with respect to x, and y squared is a constant, this will be y squared x. And now we have to evaluate this guy from x equals 0 to x equals 4. So what I'm going to do is I'm going to plug in 4 for x, and I'm going to leave y as y. I don't have anything to plug in for y right now. That will be taken care of by the outer integral. And so when I plug in 4 for x here, I'll have 1/3 times 4 cubed plus y squared times 4. And then the same thing evaluated at 0. So minus 1/3 0 cubed plus y squared times 0. And remember, we still have this outer integral here from y equals 0 to y equals 5. And this outer integral is dy. So when I evaluate that, let's see, 4 cubed divided by 3 is going to be about 21.3. So this will come out to about the integral from y equals 0 to y equals 5. This will come out to about 21.3 plus 4y squared. And that's still dy. So now we're just going to take that integral on the inside, or on the outside now, which is with respect to y, and that's going to happen much in the same respect as we would take a normal integral. So the integral of 21.3 is 21.3y. The integral of 4y squared is 4/3 y cubed. And all of that needs to be evaluated at y equals 0 and y equals 5. So I'll have 21.3 times 5 plus 4/3 of 5 cubed. Now I need to subtract away using fundamental theorem. 21.3 times 0 plus 4/3 times 0 cubed. And 21.3 times 5 plus 4/3 of 5 cubed comes out to about 273.3. Now, what are our units? Well, we have to come back up here. We didn't actually know what the units were. All we know is that this is some units of height times units of width times units of length. And if you multiply units by units by units, you get cubic units. So that's one way. Of course, we could have said, let's integrate with respect to y first. Y equals 0 to y equals 5 of the function x squared plus y squared dy, and then integrate it from x equals 0 to x equals 4 dx. So when we compute this integral, the inner one is going to be identical to the previous one we took, except now we're going to be treating x as a constant. So if x is being treated as a constant, I'm going to think about that just like I would 3. What's the integral of 3 dy? Oh, well, it's 3y. What's the integral of x squared dy? It's going to be x squared y. The integral of y squared is 1/3 of y cubed, and now we need to evaluate that at y equals 0 and y equals 5, leaving x unchanged, because the outer integral will take care of x for us. And I'm not even going to worry about plugging in 0 because I know that that whole thing is going to come out to 0. So what I will have here is 5x squared plus, if I plug in 5 cubed is 125 thirds. I'll just leave it as a fraction this time until the end. And now we're going to integrate that with respect to x, from x equals 0 to x equals 4. And one important thing to notice here is that when I integrate with respect to x, there should only be x's left in the equation. If there were still y's, we'd be in a bit of trouble because we don't have any other integrals, and that would mean that we would end up with a y in our final answer. So almost there. The integral of 5x squared, now we don't have to worry about holding anything constant, is going to be 5 thirds x cubed plus 125 thirds x. That's going to get evaluated at x equals 0 and x equals 4. And let's see, 4 cubed is going to come out to 64 times 5 is 320 thirds. So we'll have 320 thirds here. 125 thirds times 4 comes out to 500 thirds. And then, of course, we're going to subtract away 0 because we're going to be plugging in 0 for x here. And not surprisingly, 320 thirds plus 500 thirds comes out to, you guessed it, 273.3 cubic units. And so you see that we get the same answer here as we do by integrating the other way around, which is to do, initially, recall that we did the integral with respect to x first, and then with respect to y, but we still came up with 273.3 units. Now things will change eventually whenever we're not talking about rectangular regions. Right now, all of our regions that we're integrating over in the xy plane are all rectangular. So when we drew that picture, this is a perfect rectangle. Well, I didn't draw it perfectly, but it's a perfect rectangle. But suppose we wanted to actually find the volume underneath, like a triangle, for example. How would we do that? Well, at that point, how we set up our boundaries will have to change. I apologize, the video is so long, but this is all the really, really important stuff, and going forward, we're not going to be doing a whole lot of hand computation of these integrals. We're going to focus on setting them up. So you'll practice these a little bit, but then eventually you'll be using Wolfram Alpha to compute these integrals for you.